So to start off, I'm going to be talking about reinforcement learning. And I believe earlier there was a talk by Meta Reveal by Mr. or Dr. Nguyen. So you've already had a little bit of talk about reinforcement learning, but I feel like I should always show this slide where you have an agent that's going to be interacting with an environment by taking actions. And then the environment tells the agent what state it's in and gives it a reward. And over time, the agent tries to maximize that reward. This paradigm has been around for a while, and it recently been getting more and more popular, in part because of deep learning. But what I've really been interested in is thinking about not a single agent in the environment, but what happens when there's other things. So I've been thinking about what happens if there's a person in the environment. Can that person help an agent out? Or if there's one agent in the environment that has already learned something, could that agent help another agent out? Seems like a trained agent could help a novice agent. And lastly, we won't be talking about this today, but we've been doing a little work on how a trained agent could help teach a person how to do something. So let's assume that our agent is not alone, that there is something that knows a bit more. What could that more knowledgeable teacher do? Well, it turns out there's a bunch of options. So one thing we'll be talking about today is action forcing. So the teacher could just say, student, go left. And for today, we'll just assume that the student listens and actually goes left. But there's a bunch of other things you could do. You could think about augmenting the state space. So the teacher could tell the student, here's an important feature of the environment that you should pay attention to, because I've learned that this is important. So for instance, thinking about, oh, well, if you're a commuting agent, the teacher might tell you, understanding the temperature is important. Because at least in Edmonton, when it gets down to -40, you probably want to take a different route because it could be slippery and it's certainly going to be cold. You could also think about reward shaping. So you get this environmental reward that's coming down to the agent from the MDP, but you could also have the teacher giving the agent breadcrumbs, trying to lead that student agent along the path to a good reward. So for this talk, I'm going to make a few assumptions. The first one is, in general, with one minor exception, I'm going to assume that there is a single teacher, and that by and large would be a human. It could be another agent, but there's going to be one of them. And that teacher is always going to be available. Now, of course, this is unrealistic because sometimes humans wander off or they get distracted. We're going to assume that the teacher is always available and is always there to help. And the teacher wants to help. You could, of course, come up with situations that are adversarial, and you need to figure out if the teacher is evil or not. We're going to ignore that. But I will assume that the teacher is suboptimal. So in my work, I'm very interested in looking at teachers that are not perfect. So we need to understand if and when we should outperform them. Oh, good question. So in the chat, someone asked if the teacher has access to the environmental information. So I'm going to assume that the teacher has some kind of visualization, and usually that way of seeing the environment is similar to what the student can see. So you could think of cases where the student has a very low level view and the teacher has this higher level view and all this extra information that could help it help it make better decisions. But I'm going to assume the student and teacher have fairly similar state representations, so that way, hopefully, the student could always learn to outperform the teacher eventually because it has access to all of that knowledge. So thank you for the question. Keep them coming. So let me before I dive into the RL setting, let me take one step back. And I want to present 3 slides from my friend Corey. So, let me hop back. The suboptimal is, I'm assuming that the teacher is suboptimal because that just makes it more interesting. If the teacher was optimal, I would just want to learn to copy them perfectly. But I'm going to leave room for the case where the teacher is not perfect, in which case I could tell that from the environmental reward in some cases. So hopefully I can outperform them. But the things I'm talking about today should work also if the teacher is optimal. So my friend Corey is a research scientist at DeepMind, and I get to teach a graduate class on interactive machine learning. I'm pretty excited about that. I taught it last fall, and it will be next fall also, but all our material is online if you're interested. And Corey's PhD thesis was actually on using interactive machine learning for theater improv. So he got to do improv with a robot for his PhD thesis. But his main argument is that all machine learning is interactive. So you think about the machine learning pipeline. I've got some data and I go to process data, and then I've got my model that I'm learning, and there's probably some feedback or input, and then I make predictions. And what Corey's argument is, look, the raw data was collected by humans. It's probably about humans. Certainly the processing was done by a data scientist. The model we choose was an algorithm designed by humans. The input and feedback is coming from humans, and the predictions are things that we're giving to humans that humans can act on. So this struck me because this is not the way I was taught AI and machine learning. It's very much, you've got an agent that's interacting with the world, or we've got a supervised learning algorithm that's on its own, figuring out what data to use. But really, humans are in the entire loop. In reinforcement learning, I think it's a little bit different because we have an agent that's interacting with an environment. And many times we think of that agent as just doing its own thing, not getting any help from humans. But really, in a reinforcement learning setting, we want to think about the amount of bias we're putting in. So it's absolutely true that we're choosing the algorithm, we're choosing the deep neural network and the number of layers, and there's going to be some human bias, but how much bias do we want to put in there? Particularly, this comes back to the suboptimal point. If the human designer is suboptimal, then maybe some of these choices the human is making are not perfect. And maybe we want to let the agent eventually be able to outperform that human in ways that the human was suboptimal. So that's kind of the setting for this talk. Now, where I want to go is, now that I've kind of laid the groundwork, there's kind of 4 things I want to touch on. The first is looking at demonstrations. So let's say we get a data set and we want our agent to use that data set to learn or learn faster. That's one way of helping an agent. You could also think of a more interactive setting where there's a teacher. Again, it could be a human or an agent, but there's a teacher that's looking at the student agent and jumping in and giving advice and trying to help out on the fly. The third part is talking about human feedback. So when I say feedback, think of training a dog. You could say good boy, bad boy, good robot, bad robot. And it turns out you can absolutely teach agents and robots that way, but good robot can mean different things to different people. And there's different ways of interpreting that, which is getting back to where humans are messy. Humans are confusing. How do I figure out what the human's actually trying to tell me? And lastly, if there's time, I'll touch on some explainability work and posit that explainability should help all of this. If you've got a human in the loop, seems like if the human could better understand the agent, it seems like that would help the human give better feedback. So that's where we're going. Oh, excellent. So there's a question about what's the difference between feedback from the environment and feedback from the human. So in general, in an RL setting, you assume that feedback from the environment is perfect. It's absolutely true. That's what you want to maximize. Whereas feedback from the human could be misleading, could be wrong. Also, the feedback from the human could be numeric. It could be categorical. So we'll get into that a little bit more in this other part. That's a great question. Okay, dramatic pause to see if there are more questions before I hop into demonstrations. All right. And for anyone who joined us late, remember that you are free to unmute and ask questions at any time or drop them into the chat. So when I think of demonstrations, one of the ways you can get demonstrations is just have someone play a game. Let's say you could have them play Atari, have them play Mario, just sit them down and let them control the robot. But whatever we do, we can get those demonstrations. So let's say there's someone sitting at a keyboard, and when the agent is in a state, the human tells the agent which action to take. So you get a bunch of these state action pairs, and this demonstration is just a set of data. It's a bunch of states and actions and a policy in reinforcement learning. A policy is just a mapping from states to actions. So we can use supervised learning to say, I've got this human demonstration. Now let me summarize that as a policy. In this case, this work almost 10 years ago now, what we did is we used a human interpretable supervised learning method. So we could learn, try to estimate if this agent was in this state, what action do I think that the human teacher would take? Normally in reinforcement learning, you trade off exploration and exploitation. So exploring, trying to find something better, exploiting, do what you think is best. Now, in addition to exploring and exploiting, we could also execute the human's policy, or rather, execute what we think the human's policy would be. So initially, I'm going to execute a lot. Initially, the agent's going to try to follow the human's policy, and then with some probability it can explore, and with some probability it can exploit. And then over time, I'm going to turn down that knob so we rely less and less on the human because we're assuming the human is suboptimal. If the human was optimal, even then, we've got a finite data set. So with a finite data set, our policy that we're learning will not be perfect. So even then, we're probably going to want to gradually listen to our estimate of the human's policy less and less. Great. So how does this work? Here's a game of keep away, where the 3 agents in red are trying to maintain possession and the 2 agents in blue are trying to get the ball or kick it out of bounds. So the human's demonstrating, and you can see the game is relatively fast. It takes a little while to get a handle on how to actually play this game. And it's not trivial, particularly since when the agents pass, there's always a chance they're going to miss kick and it's going to go out of bounds, or the agent is going to receive the pass poorly because of noise in the simulated sensors and actuators. Anyway, the human plays, we summarize the policy, and then we use this explore, exploit, execute to better learn from the human. So we're going to use these demonstrations to learn an estimate of the human's policy, and that will bias our policy, the agent's policy. Great. So here's a normal reinforcement learning curve. In the red, we have learning from scratch. And in the orange, black, Halloween themed line, we are learning with the demonstrations. So there's a few ways you could look at this. We could look at the initial performance. That's very similar, the jump start. We could look at the final performance. Ours is a little bit better. We could look at the area under the curve. Ours is a little bit better. And then you could be kind of cynical and squint at that diagram and say, okay, Matt, I see why there's just statistical significance there, but those lines are real close. Why would I practically care? Well, one measure of performance is looking at time to threshold. So if I said, I really want my agents to train until they get to a performance of 14. Well, if I train from scratch, it takes around 14 hours. If I train using demonstrations, human demonstrations, it takes about 8 hours. So that's pretty cool. 14 hours to 8 hours. That's a pretty significant savings. And we get this savings with only using 3 minutes of human demonstration. So I'm saving almost, what did I say? So I'm saving a bunch of more than 5 hours of training. by just using 3 minutes of human time. So that's what I think is really exciting about human in the loop reinforcement learning, that with just a little bit of human bias, you can make huge improvements, huge savings in time, and still outperform that human. So this was the result about 10 years ago that really got me into this area. And of course, since then, there's been a lot of interesting things. One method I'll mention that came up recently was from Daniel Kidenko and his colleagues, where they had multiple experts. So this is the one time I'm relaxing that assumption. I'm going to, for the next 2 slides, let's assume I've got multiple people shouting at me. And what they did is they said, let's say I've got 3 experts. I'm going to learn a maze. Expert 1 is only good at the left part of the maze. Otherwise, he's random. Expert 2 is only good at the middle part of the maze. Otherwise, it's random. And expert 3 is only good at the right part of the maze. Otherwise, it's random. And what they were able to show is that their agent could figure out which expert to listen to in which part of the state space. And that I thought was really cool, because think about learning to play Mario. So you can have one expert that's really good at doing speed runs, one that's really good at getting coins, one that's really good at killing enemies. And maybe you want to figure out who to listen to when, or how to balance them. So this is an area where there's been a little bit of work, but there's a lot of open work there. And now I've got a slide with a green border, which means it's a reminder to me that this is something that we're still working on and is not published. But one of the things we're working on is trying to look at what happens when the experts are actually bad. So figuring out, if I've got 3 experts and 2 of them are trying to mislead me, what could I do to try to avoid that? Yeah, go ahead.
A small question. In this particular case, I may also use mixture of experts, the old work of Michael Jordan. So in this case, could I have the same results at the end?
So Michael Jordan's mixture of expert stuff?
Yeah.
Yeah, so does that actually apply in the reinforcement learning case? I guess I'm not remembering the details.
No, that was, it didn't use reinforcement learning. It just used, as the previous slide, different experts. And he had a get network to learn which expert is good in which situation.
Yeah, so I know that's been done in the supervised case. One of the problems, one of the things that makes it tricky in the reinforcement learning case is it's hard to tell what an expert is, because there's no correct answer, and you take actions. And so, for instance, so let's say I am following expert 1, and that's great. Expert 1 is telling me the right thing. But then I mess up in the other part of the maze and never get to the reward. In that case, because of this sparse reward setting, you might not be able to figure out who I should listen to until way down the line when you get the reward. But I'll also point out, though, that reinforcement learning has a strong and storied tradition of stealing ideas from supervised learning. So you're absolutely right that one of the things that we RL people are always doing is trying to look at the supervised learning literature, or unsupervised, and trying to figure out what ideas there can we mine for our setting.
Okay, thank you.
All right, and so we could have multiple experts, but this was one way of thinking about demonstrations. Another idea came up also in 2011. And here the idea was, well, I could have a demonstration, and I've got an expert that's demonstrating how to drive a car. At some point, the car, my agent trying to follow that demonstration, is going to deviate slightly because it's not perfect. It's going to deviate slightly and get to a state that the expert never demonstrated because the expert didn't screw up. And this is the idea behind Dagger, where with Dagger, you get a bunch of demonstrations. The agent tries to follow those demonstrations, tries to follow that policy, gets off the beaten path. And then you ask the person, what would you have done here? I messed up here. What would you have done? Then you get more data, retrain, try to follow the policy, and then you mess up in a different place. And then you ask again, can you help me out? So in this case, the agent's able to learn because they're able to ask the human for demonstrations more and more. And the way it asks for demonstrations, or where it asks for action advice, is where it thinks it messed up, where it doesn't know what's going on. And this is a really cool algorithm. If you're interested in learning from demonstrations, this is one of the first papers you should read. But I'm going to argue that we can actually do things better. We can do better than just having to ask repeatedly, hey, human, can you give me more demonstrations where I messed up? So that was my bit on demonstrations. Now I'm going to take another drink of water and see if anyone else would like to unmute or drop anything in the chat. Okay.
Maybe
So
just a last question. In 2 or 3 previous slides, you presented a curve where the final performance of the reinforcement learning was higher than the no prior, but maybe just because you didn't give any times for the training time. But if I have a lot of time to train, does these 2 curve reach at the end?
Yes. So if I go to about 50 hours, they do end up converging. So in general, I don't want to claim that humans will help the RL agent get to a better asymptotic performance. But hopefully the humans can help agents get to a better performance faster. Now, this gets a little bit hand wavy because as soon as we go into nonlinear function approximation, we're not guaranteed to converge to the optimal performance. So if I'm, say, using deep neural networks, there is a chance that the humans would let us find a better policy that the non-biased agent doesn't happen to find. But in general, that's hard. That's not something I would bet money on. Instead, I would guess that assisted and unassisted agents would eventually converge to the same performance. That's a great point. This graph is a little misleading because I do not go all the way out to show convergence.
Thank you.
I have one question, maybe 2 or 3 slides later. Yes, here. So when, last slide, previous. Thank you.
Previous?
No, when you talk about the bad expert. Oh yes, this one. Yeah. So my question is, how do you define a bad expert? Do you give this information to the agent, or the agent needs to find if the expert is bad by itself? And if it does, how does the agent do this? Yeah.
Yeah, so we purposefully do not tell the student which experts are bad. And you could think of a bad expert as being random, as having a decent policy, but making some mistakes. You could even think of an expert as adversarial. So I'll try to give you some good advice, and then I'm going to turn on you and make you do horribly. And the current state of the art, no, I shouldn't say that. The current state of our research is we're not exactly sure how to do this. We do have some ideas. And a lot of it relies on trying to figure out where the experts are going to be good and where they're bad, but also trying to generalize that. So if we see, if we're in a car driving simulation, if we see an expert that's trying to make us drive the car into a tree. If we see an expert that's trying to do something malicious in one part of the state space, we're probably not going to trust it so much in any part of the state space. So that's one heuristic we could use. But in general, it's a pretty difficult problem.
Yeah, yes, I think one of the possibility to see that is through the reward function. So I think it's the reward function tells you if you are doing good or bad. So actually, I feel like we are putting all the all the pressure on the reward function. So what happened if I can't define a good reward function?
Oh, so if you can't define a good reward function, then you're in a lot of trouble in a reinforcement learning setting.
Yeah.
And that's actually a great point, because that's something a lot of reinforcement learning people overlook. We as a community generally assume someone hands you an MDP and it's perfect and the reward is perfect. But when you work with companies, when you work in the real world, no one hands you an MDP. You have to design that MDP. You have to design that reward. And that's something that we as a community need to struggle with more. Where does that reward come from?
Mm-hmm. Okay, thank you. Maybe I have other questions I will ask later.
Okay, yes, please do.
Thank you.
Can it also be the other way around, that the expert is very much correct and that maybe we could not design a reward function that is always good? I also think of this from a usability perspective. If I am the expert and I say, do not do this specific error anymore, then I do not want the model to do it anymore.
So two thoughts. One is that's where inverse reinforcement learning could come in. So if the expert is able to give optimal demonstrations, then we can use inverse reinforcement learning to say, what is the reward that this expert was optimizing? That's one way of doing it. A more realistic, because experts still, even if they're experts, they might not be optimal, perfectly optimal. A more realistic thing is to think about defining an MDP as an iterative process, that the domain experts sit down with the ML nerds. They write down an MDP, the agent solves the MDP after a lot of time, then the domain experts come back in and say, no, that's all wrong. And then the nerds like me said, well, I did what you told me to. So then you've got to iterate. Maybe the state space is slightly wrong. Maybe you're not considering the right actions. Or like you were saying, maybe the reward we defined isn't perfect. So it's in the real world, it's got to be that kind of iterative process, I claim, because no one hands you an MDP.
Thank you.
All right, so let me hop into the thinking about targeted actions. So, good question. Sorry, there's a few more. I think we've followed. Okay, then the last question was, should the experts also not only suggest good actions, but say what you shouldn't do? And you're absolutely right. There are cases where there's been some interesting work where experts will say, do not do this, and that can help. There's also some interesting work where experts get the agent to do something really bad very early in learning. So if you have a virtual car and the human tells that virtual car to run into the virtual tree, then you get a lot of negative reward on that one episode. But then maybe the agent, the student agent, can use that knowledge to now know, oh, I better stay away from all trees. Good thing I learned that really early in my training. So I'm mostly focusing on the teacher giving good actions, but you could absolutely look at things like teachers saying, never do this. That's a great point. So this setting I want to switch to is saying I have a student, and that student is, in this case, playing Pac-Man. And in addition to the student, I also have a trained teacher, similar to what I was doing before with the demonstrations. But now the teacher has a budget. The teacher can only interrupt so many times. One justification for that is, well, if the teacher could always interrupt, then the teacher could just tell the student exactly what to do, and it's not a very interesting problem. Another justification, though, is if you have a person as a teacher, that person is not going to be infinitely patient, will not give the student an infinite amount of advice. Nice side effect is that with this budget, then a suboptimal teacher will not be able to force the student to do exactly what it wants. Instead, the student can use the environmental reward to outperform the teacher, because eventually that teacher has to shut up. So we looked at Pac-Man, and we said, I'm going to have 500 episodes of training, and these episodes are up to 2,000 steps in length, but my budget is only 1,000 actions. So I can give advice for less than half of one episode. And this video is not playing very well. But now the question is, with demonstrations, we could just have people give a large number of state action pairs across the state space. Now we want to be very careful about where we want to target this advice. So the first thing you might think of, the simplest thing you could think of, is let's dump out all our advice at the beginning. Reinforcement learning agents start from random. They're real dumb at the beginning. So why not give all of my advice at the beginning? One option. Another option is to think of, I want to give advice where I think it's important. So I look at how important is the student's current state. If the state is important, the teacher could give advice. Okay, great. What does important mean? Well, one way of defining state importance is to look at the difference between the best and the worst action. So on the left here, I have a high importance state. If I go to the right, I die. If I go up, I get a food pellet and I don't die. So the difference in how good those two different actions are quite high. But on the right, it doesn't really matter. I'm not about to die. I could get food if I go up or to the right. So this is one heuristic, a heuristic for when the teacher should intervene and say, student, don't mess up now. I'm going to tell you what to do. Another thing you could do is, in my diagram, I showed the teacher talking to the student. We could cheat and let the student talk to the teacher and say, hey, teach, I'm going to go up. Is that okay? And then the teacher, if the student gets it wrong and it's an important state, then the teacher could say, no, don't go up, go right. Oh, good question. Who's going to give the max? Let me jump back to that. This is important. I am considering state importance from the teacher's viewpoint. So I'm assuming a teacher has already learned Pac-Man, and in this case has learned an action value function and can estimate the difference between a good and bad action in a state. The student, it would be very hard for the student to understand, is this state important? Because the student is going to have pretty bad Q values initially. So this is all from the teacher's perspective, that the teacher has already learned and is deciding when to intervene. So if the teacher had not learned well and the teacher's Q values were not very good, then this heuristic would not work either. So I could do mistake correcting, where I require the student to yell every time it's going to take an action, and then the teacher listens to what it's yelling and then can intervene or not. Or instead of making the student yell, we could have the teacher model the student. So now the teacher's looking at the student. If the student is in an important state, and if the teacher thinks the student is going to mess up based on their model, then it will intervene. So these are 4 heuristics. These are 4 heuristics for how we could teach. So first, we've got our learning curve. This is learning Pac-Man with no advice. And since it's a paper that was published, as you can guess, our method did better. So the orange line actually does quite a bit better. And you can see at the beginning, if we look at around the 0 training episodes, early advising starts off a little bit higher because the teacher is telling the student what to do, and the student just follows that. But then it kind of unlearns, but oh, that bias was good enough, I can learn faster again. And then the other 3 curves, importance advising, instead of jumping all of the advice at the beginning, if I give it an important state, that helps. If I do mistake correcting, I do better. And it turns out in this case, the teacher's model of the student was good enough that predictive advising does as well as mistake correcting. So this shows that if we have a trained teacher, we can figure out where to give advice, just a small amount of advice. Remember, this is 1,000 pieces of advice, which is less than half of one episode, to make a significant improvement in performance. And I'm not showing it on this graph, and the student can learn to outperform the teacher. So here are these 4 ways of advising, 4 heuristics for how the teacher could help the student learn. But all 4 of these, the student gets this information from the teacher, acts on it, and then discards it. And that seems kind of silly, right? You've got this information from the environment, rewards from the environment, but if you're getting an action suggestion from the teacher, that's actually quite important. Seems like you could do something more with that. So I was excited when last year at AMOS, Ergeman and his collaborators put out this paper. And okay, one of the reasons I liked the idea is that my own student was working on it. So in one sense, we got scooped that they came out with the paper first, but it is a cool paper. And what they do is they say, I'm going to use early advising. So I get advice from the teacher, but the student, instead of just using that advice, instead tries to model the teacher. So remember when I showed you the learning from demonstration, where I said, I've got a policy that will estimate what the human would do based on demonstrations. Here, they learn a model. They learn a policy based on what they think the teacher would do. So now, after they've used up all the teacher advice, now they've got a model, and they've got a way of estimating uncertainty in that model or that policy. And when the uncertainty in that policy is low enough, they do what they think the teacher would want them to do. So in this case, the student has a model of the teacher and is able to leverage that model even after the teacher stops talking. So I was pretty excited about that. And luckily enough, Ergeman, after I saw this awesome paper, I wrote to him and he was like, yeah, your paper is really cool. Hey, do you want to work together? So Ergeman has been collaborating with us, and my student Sahir has this paper that we were trying to submit to AAAI. We missed the deadline, but we've got some initial results where, in addition to modeling the teacher, we also think about uncertainties. So the student has an uncertainty in its own model, and there's an uncertainty in the teacher's model. So if the student is uncertain, if the student doesn't know what to do, then let's see if my model of the teacher is good enough. If my model of the teacher is good, then I can follow that model. If it's not, then and only then do I go ask the teacher for advice. So the idea with this ongoing work is trying to limit asking the teacher. You're trying to save up that advice. So instead of the teacher deciding where to give advice, in this case, it's the student saying, I'm confused, please help me out. So this is an active area of research. If you're interested in this, I think the idea of thinking about where the teacher should proactively help the student versus where the student should ask for help is really interesting, because the teacher knows you assume the teacher knows the environment, the task better, but maybe the student better knows what it doesn't know. So there's this interesting interplay where some cases, I believe this type of teaching should be student driven. In other cases, it could be teacher driven. So now is another great place for me to pause and ask for additional questions or comments. You guys have been doing a great job shouting out. I do appreciate that. All right. My talk today is supposed to be about what is the human trying to tell us? And in this third setting, I want to consider the case by and large where there's no environmental reward. So now I'm gonna break the MDP setting. I'm gonna say there is no environmental reward. I only have what my teacher is telling me. One of the first works here was from 2006. And instead of an environmental reward, people gave the, I believe it was a +1, a -1, or 0. So they just gave those numbers, gave that as feedback, and Andrea and Cynthia treated that as the environmental reward. And one of the things that was weird is that people were giving kind of predictive feedback, that they were giving +1 when they thought the agent was about to do something right. So this was a case where even though the instructions said one thing, people wanted to do something else. And in their paper, they came up with a clever trick to fix that. But this was one way of incorporating human feedback, just treated as the reward signal. Then, a few years later, Brad, Peter, and some others came up with Tamer. And this is kind of a complicated diagram, but the important thing here is the human gives some feedback, and then Tamer tries to learn what actions should I take in order to get feedback from the human. Now, one subtlety here is in Tamer, they're treating the feedback from the human as a return. So the return is the discounted sum of rewards from now until infinity. So a reward is a one-step transitory thing, whereas the return is all the reward I'm going to get in the future. And what Tamer does is says the human is telling me how well I'm doing going out into the future. So it's not the immediate one-step reward, it's really how well am I doing? So all I need to do is maximize this one thing using supervised learning. And this method works quite well. And here's a fun video. Oh, the video isn't playing very well. That's okay. So on the left, you see during training, and you can see, maybe you can see there's a black cube in the upper right, which flashes red and green. And it's during training, it's not doing so well. But on the left, you'll see that after just 2 games of training, the agent's performing quite well. And even if you can't see the video that well, one way of looking at this is the number of lines is quite small on the right. If you've ever played Tetris, you can see that the agent on the left is doing much worse. So after just a few minutes of training, you can get great performance, even without an environmental reward. And what Tamer does, going back to that diagram, Tamer is treating the human feedback as a number and treating it as a return. It's trying to maximize. Another thing you could do, in 2014, Robert and Michael Littman and Dave Roberts and Bei Peng and I looked at what if we don't treat it as a number, what if we treat it as categorical feedback? So if we say, we were very dog inspired. So if we say sit and the dog shakes, say bad dog. Why is that a -1? Why isn't it a -5? Or if we say sit, the dog sits, and we say good boy, why is that a +1 or a +10? So instead of treating this as numerical feedback, instead we use a Bayesian approach and treat it as categorical feedback. Now I'm going to just skip over the details other than saying that, first of all, it worked. But one of the interesting things we found, and this is why human subject experiments are so critical, is that different people teach differently. So let's see, for instance, some people, when the dog did the right thing, they said good dog. When the dog did the wrong thing, they said bad dog. A larger group of people, when the dog did the right thing, they said good dog. When the dog did the wrong thing, they said nothing. And this is actually how you normally want to train dogs. You don't want to yell at your dog or hit your dog when he does the wrong thing. Instead, you just want to focus on positive reward. So in this work, we not only showed that using categorical feedback made sense, but also that different people did teach differently. And if you account for that, if you learn how they're trying to teach, you can absolutely do better. Now, the last thing I'll mention is Coach, which was led by James with mostly the same group of people. And here we were saying, is the feedback really based on what just happened, or is it considering more than that? So this is the last experiment I'll show, where here we have a dog that needs to do something. And the person can give it punishment or reward somewhere on a sliding scale. So this is the grass. We don't want the dog on the grass. We don't want the dog to pee on the grass, but we do want the dog to get to the goal. So we could consider three cases. The first is bad. The dog walks right over the grass and gets to the goal. That's bad. Then there's a medium condition, an all right condition, where the dog does not walk over the grass, but it's also suboptimal. And then you could have the good case. This is the optimal case. So we had these three conditions. And then what we did is we had people in each of these three conditions witness bad, bad, and all right. Second condition, all right, all right, all right. Third condition, good, good, all right. So in the first case, the dog is bad and then gets better. Second case is continuous, or the same. Third case is the dog's doing well and then doesn't do quite as well. But the important point is, what we're going to do is ask for feedback when the dog is doing this middle condition. And what we see is when the dog is improving, when the dog was bad to the middle condition, it gets much better, much higher feedback than the other two cases. So this is empirical evidence that people are giving feedback not just based on what happened right now, but relative to what was happening before. So looking at the trajectory of the performance improvement. So this is another way that you could interpret human feedback. And the critical thing here is we don't always know which one is best. So this is very much what I think is an exciting area of open research. I'll just mention this. We have, Callie has some ongoing work where we are looking at trying to teach the person how to teach. Yeah, if you've got an agent and you know how that agent learns, it makes sense that if the human understood more about how that agent learned, it seems like the human should get better advice. And we've got some preliminary results on that. Yes, thank you, Vincent. Sorry, Vincent's message was I'm almost out of time. So I'm going to mostly skip over the last piece. I'm just going to hop to the open question. So we did some work on explainability, and we're hoping to publish that soon. Let me hop to this. So the thing I want to mention is explainability should be really useful for humans teaching agents. And when you're thinking about explainability, you need to think about who is the explanation for, what is it for? And one of the things we found, which is not too surprising, is that people's perception of how good they thought they were. People saying, oh yeah, I'm really sure I know what's going on, is not really correlated with their performance. So I can't remember the exact number, but I think in the US, something like 70% of drivers think they're above average. So clearly people are not always good at estimating their performance, but this is another example of where you probably shouldn't rely on humans' interpretation of their understanding. And we're currently working on, Sean is currently leading a project on trying to understand if and when giving explanations to a human teacher lets that human teacher give better advice. And this is a really ugly diagram or picture that he just sent me yesterday. So he's going to be unhappy that I'm showing it, but he's making some cool progress on figuring out where and how explanations can help. All right, so wrapping up. One of the projects I'm working on and excited about is trying to figure out where these different kinds of human advice can help most. So I think we talked about demonstrations, action advice. We could think about humans giving representations. We're doing some work on humans giving code sketches. And we talked a little bit about feedback, but figuring out where a person can give the most help. So if they can't program, we probably don't want them writing code. If they can't perform the task well, we probably don't want them giving real-time demonstrations. But figuring that out is ongoing. And the last open question slide is, so thinking about where are people better or worse at teaching? That's what I was just talking about. What are their preferences, which could be different than where they're best. But remember, I was talking about that at the very end, the student trying to ask for help. I think this is going to be really important. If the agents can better know what they don't know, that's going to be huge for helping the student better ask for teacher help. And I think explainability is going to be really important here. So with that, I will show one slide saying, if you are interested in human-in-the-loop reinforcement learning, I suggest you check out HippoGym, the human input parsing platform for OpenAI Gym. It's open source, we just released it, and we're looking for more people to onboard onto the platform. And the idea is that you can perform human subject experiments over the internet easily, especially important during COVID. All right, with that, I will stop. And I believe we have about 3 minutes for questions. So you all did a great job for interrupting me during the talk, and I do appreciate that. But if there are any remaining questions, now would be a great time to ask them out loud or drop them in the chat.
Yes, don't hesitate to raise questions. Maybe I have one question. If you go back to the slide where you showed the performances on the Pac-Man game, you have an orange curve and maybe a blue curve.
Not this one?
No, it's a Pac-Man game. Yes, you presented results from different strategies. You had an orange curve. It's the second one.
Maybe this one?
Yeah. If I see there is like a dip in the curve, because at the beginning you have good performances and the performance decrease, and again it becomes good. So it seems like in active learning that you discover something in the space of the, but in your case, you have the teacher which know everything about the game. Could you explain this dip in the curve?
Short answer is no, I can't explain the dip. I can say that when I was doing transfer learning before this, we often saw in transfer learning, you would get this same kind of dip. And one thing to note is by 100 episodes, all of the teacher's advice budget has been used up. So when we see this dip, there's really not anything the teacher could do about it because they already used up all their budget. But it is really interesting that in multiple domains, multiple methods, we see this big help and then this unlearning and gradual recovery. And you could think, you could say, well, okay, reinforcement learning is supposed to explore, so it's going to go and spend some time on suboptimal things. But it's still weird that we see such a large effect. And this is averaged over, I think, 30 trials each. So this is not just a statistical fluke. The agents are actually unlearning. And if we could figure out how to avoid that, or even at least justify why it's unlearning, I'd be very interested in that. And it's not just my work. I've seen this in other people's work too, in transfer learning and teaching, where it goes up, you see a little dip. And so far, we don't have any explanation. So if anyone has suggestions or insights, I'd love to hear that.
Thank you.
Maybe I can refer to that, because I saw that in active learning applications as well, especially when we were working with some kind of optimal strategy, which is maybe related to this supervising component from the teacher, because he also has some very clear image of how the student should behave, maybe. And we had that problem with something like a greedy approach, where it relatively fast come to a very good solution, but in order to get even better, it has to, or the good solution is just a very broad approximation. We work in classification of the decision boundary, for example. But to get better, it has to pick other instances in our case that first will lead to a decrease in performance, because then it is possible to learn the decision boundary better. So what helped in our application is to implement something like a look ahead. So to look into the future, to include more a long-term view. And this actually led to the case that we accept short-term decreases, but we know that after like 5 acquisitions, or in our case, it was just 2 acquisitions, we will go up again. So it is not such a big drop then, or even stagnation, because it's not possible to get away from that suboptimal solution. So that is what my experience, or our experience, was regarding active learning. Maybe that is something similar here.
I love that explanation. Is there one particular paper I could look up?
My dissertation. It's not yet. Okay. It's not yet published. I can send it to you, because it's also not yet published.
Yeah, once you can send it to me, I'd love to look at that chapter. That sounds really relevant.
Yeah, I can absolutely do that.
Yes, I agree with Daniel, because it's a problem of exploration and exploitation, I think. And by having a long-term view, you are able to explore a little bit to prevent this kind of behavior.
Very cool.
Maybe other question from the audience?
I don't see anything in the chat.
No. Maybe I have maybe not a suggestion, because I'm not sure to be able to give you a suggestion. But in your last slide about future works, when you spoke about interpretability, where does explainability help teaching? Maybe a way is to try to perform your first training without using all the budget you have, for example, for given of episodes, and then to interpret the result to design a better reward. And by this way, having a better reward, you will be able to learn a new kind of task, or something which is easier or better to learn. I think that's the case with your dog, because if you said no, that's the right way or the bad way to go to not walk on the grass, but you say okay or not okay. It's like you interpret your results. If you say there is not a better way, this is another way. And it's like if you find the best way to discretize your rewards, to find the best intervals to give in the reward.
Yeah, and I think I guess so. Let's see. There's a few things I want to unpack there. The first is let's assume the person is really good and understands the task better than the agent, then I think doing this kind of iterative thing would absolutely help better define the reward or better define the correct MDP, and have that kind of iterative process where I believe explainability would absolutely help. Because if you can't see what's going on inside the head of the agent, it's going to be much more difficult to understand what it's doing wrong or why. So if I think about teaching as not just getting my agent to do better in this task, but also better defining the task that I actually want it to do, that's really interesting.
Yes, not only better define the task, but also better define the reward, I think.
Yes. Oh, sorry. I was using reward as synonymous with task and state.
Okay.
And yeah.
Okay. Thank
Yeah.
you.
Perfect. Yeah. Well, actually, one more thing I'll riff on just briefly. The environmental reward can be quite sparse. If we can learn a more dense reward, a shaping reward from the teacher, that can help the agent learn much faster. So if
if you have a good way to discretize the intervals of rewards, maybe you are able to find an interval which is piecewise constant in the sense of the reward. And by the way, it's easier to learn after.
Yeah, I like that idea.
So any question? So if we have to stop, sorry, Matthew, thank you so much for your interesting talk.